The next we are having a Kohlrausch law. The Kohlrausch law is again about the which again talks about the the solution at an infinite condition. Now at infinite condition means after a large number of dilution, I said that we get a molar conductivity at infinite dilution after a large number of dilution, and it is a condition when there is no interaction between the Na plus and Cl minus. I said that in the beginning when Na and Cl, when sodium chloride dissociate produces Na plus and Cl minus, and then at that time there is some weak interaction between them, but during the dilution this interaction also breaks and ultimately these Na plus and Cl minus ions gets free. In the beginning, the conductivity of Na plus was get affected by the Cl minus ions, and the Cl minus ions conductivity was get affected by the Na plus ions. But after large number of dilution, means when we get the molar conductivity at infinite dilution, at this value there is no interaction between the Na plus and Cl minus ions. Means when Na plus ion moves to the cathode and Cl minus ion is moving to the anode, then neither the speed of the Na plus is affected by the Cl minus ion nor the speed of a Cl minus ion is affected by the sodium ions, as there is no interaction between them, that is Na plus and Cl minus ion. So here I can say that suppose if the conductivity of a Cl minus ion is 40 with sodium ion at infinite dilution, and here I am considering KCl, another solution, that is K plus and Cl minus ion, K plus and Cl minus ion. Then in this case, that is a K plus and Cl minus ion, the conductivity will depend on K plus and Cl, and again there is no interaction between them. So again I am talking about the molar conductivity at infinite dilution. Then in that case, if the Cl minus ion conductivity is 40 here, then the Cl minus ion conductivity will be 40 in this case also, because the Cl minus ions conductivity is not affected by the ions, whether it is sodium ion or it is potassium ion, as there is no interaction between them. But if there is an interaction, then Cl minus ion value conductivity in respect with respect to the Na plus ion and Cl minus ion conductivity with respect to K plus ion is a different. But when I am talking about the infinite dilution condition, then that case there is no interaction between Na plus and Cl, therefore so the chlorine ion conductivity is same whether it is a sodium ion or potassium ions. So the same is a Kohlrausch law. The law states that at infinite dilution each ions migrate independently of its coion, migrates independently of its coions. As I said that Cl minus ions will move independently of its coion, whether it is Na plus or potassium ions, its conductivity is going to be same when the condition is infinite dilution, that means after infinite dilution, and makes its own contribution to the total molar conductivity of electrolyte. Makes its own contribution means, suppose if I am writing the molar conductivity of NaCl, then molar conductivity of NaCl itself do not conduct electricity, but here the electricity is conducted by the ions of NaCl. So sodium ions and Cl minus ions conductivity, that is molar conductivity, is going to be the sum of these two, that is the conductivity of Na plus and Cl minus, and that's why it is said that makes its own contribution to the contribution to the total molar conductivity of electrolyte irrespective of the nature of ions with which it is associated. So the contribution of Cl minus ions will be same in case of NaCl as well as in case of KCl at infinite dilution. It does not depends upon the presence of its coion, that is whether it is Na plus or Cl minus ions, the conductivity Na plus or K plus ions, the conductivity of Cl will be same. Similarly, I can say for sodium, the conductivity of sodium ion at infinite dilution will be same whether it is associated with the chlorine ion or it is associated with the fluorine ions. Conductivity will remain constant for the Na plus ions. So at infinite dilution, the law, again I am saying a law, at infinite dilution each ions migrate independently of its coions. Its conductivity is not affected whether it is associated with any type of ions, means nature of the other ions. So here I can say that lambda of NaCl, molar conductivity at infinite dilution of NaCl, depends on the electrolyte conductivity depends upon the contribution of their ions, that is lambda naught of Na plus and lambda naught of Cl minus. Similarly, if I have lambda of KCl, then molar conductivity of K plus molar conductivity of Cl minus. In both the cases, the conductivity of chlorine is going to be same. If the contribution of chlorine is here 40, then here also it is going to be 40 only. Similarly, if I am writing the molar conductivity of MgCl2, that is magnesium chloride, then it is going to be conductivity of magnesium ions plus the conductivity of chlorine ions. But there is a double chlorine ions, that is a 2 chlorine ions, so it is going to be 2 into the conductivity of chlorine ions. Similarly, if I have aluminium chloride, then it is going to be a sum of the molar conductivity of aluminium 3 plus 3 times of molar conductivity of Cl minus. When we write the molar conductivity of a full electrolyte, then complete electrolyte, then we make represent it by the capital lambda. But when we write the molar conductivity for ions, then we represent it by small lambda. Okay, now let's see the application of Kohlrausch law. Let's see the application of a Kohlrausch law. First application, it is used for the determination of molar conductivity at infinite dilution or zero concentration, weak electrolyte. See, I said that suppose if you wanted to know the molar conductivity of electrolyte, then there are the two methods. The number one, either you keeps on diluting so that you will get a constant value, and that constant value is going to be a molar conductivity. Or the second method is that we just use that Onsager equation, that is we follow that graphical method. But at the same time, that graphical method also have a limitation, that graphical method is applicable or it can be used only for a solute electrolyte which are strong. That means which dissociate completely, because for a weak electrolyte, the graph which we were getting, that graph was in a curve shape. That means, and if it is in a curve shape, then we cannot use that extra flotation method. So Kohlrausch law now help us to determine the lambda naught value of weak electrolyte. Lambda naught value of weak electrolyte which cannot be determined from the graphical method. So suppose here I just wanted to know the lambda naught value of acetic acid. Acetic acid, which is considered as a weak acid, its molar conductivity is to be determined. Being a weak acid, it is going to be a weak electrolyte. So to get that lambda value of this weak acid, the condition is that here find out here first, to get that weak electrolyte conductivity, we will consider some strong electrolyte and we will measure its molar conductivity from the graphical method. So the strong electrolyte which is required here, the first one is so these are the three electrolytes: sodium acetate, HCl and NaCl. Sodium acetate and NaCl are the salts, so they are strong electrolyte, and HCl is a strong acid, so again it is a strong electrolyte. So here these are the three electrolytes since they all three are strong, therefore we can get their lambda naught value from the graphical method. So I calculated the lambda naught value for this as well as for third one. So I know the lambda naught, that is molar conductivity at infinite dilution for these three, and I have to calculate the lambda naught value for this weak electrolyte. So suppose if you know the value, suppose the value is 40, this value is 50 and its value is 60. And now I just wanted to know the molar conductivity of weak acid, that is acetic acid. So simply I will say that add these three electrolyte, add or subtract these three electrolyte in such a way that their ions should cancel each other, and finally I will get the ions which are present in acetic acid. You have to add these three electrolytes, add or subtract these electrolytes in such a way that after the addition or subtraction, you will get only those ions which are present in acetic acid, and acetic acid which contains two ions, that is acetate ion and H plus ion. Sodium acetate, its conductivity will depends upon its ions, that is Na plus and acetate ion. HCl conductivity will depends on the ions, that is H plus and Cl minus, and its conductivity will depends on again ions of NaCl, that is Na plus and Cl minus. So you have to add or subtract so that you will get you should get this acetate and H plus ion. So simply I will say that here I am going to add these two, because on the addition from here I will get acetate ion, from here I will get H plus ion. But here in addition to acetate ion we are getting Na plus, which is an extra part. Here we are getting a Cl minus, which is again an extra part. So to remove that Na plus and Cl minus, we will subtract NaCl from this. So the first two will be added, plus lambda naught of HCl minus lambda naught of NaCl, which can be written as molar conductivity of an electrolyte depends upon its ions, like NaCl depends on Na plus and Cl minus. So similarly here I can write its conductivity depends on acetate ion and Na plus ion, plus lambda naught of H plus ion plus lambda naught of Cl minus ion minus lambda naught of Na plus ion minus lambda naught of Cl minus ion. So finally we will have the sodium ions. We are talking about the molar conductivity at infinite dilution. So at infinite dilution the conductivity of ions remains same, and it is not affected by the presence of other ions. So that is by the Kohlrausch law I can say. So the sodium ion's conductivity will be same whether it is associated with the acetate ion or it is associated with the Cl minus. So Na plus conductivity is same in both the cases. So lambda naught of Na plus will get cancelled. Similarly I can say lambda naught of Cl minus will also get cancelled. So finally we will have acetate and H plus ion, and which is nothing but equal to acetic acid. So we are getting the molar conductivity of acetic acid by addition of these two and the subtracting NaCl. So if you want to know the value of acetic acid, then the way the addition or subtraction has been done, carry out the same thing with their values also. So these two are added, so their values will be added, that is 40 plus 50, and NaCl is subtracted, so minus 60. So 90 minus 60, that is answer is going to be 30. That is molar conductivity of acetic acid. So this is the first application of the Kohlrausch law, that here with the help of Kohlrausch law we can calculate the molar conductivity of weak electrolyte whose lambda value cannot be calculated by using graphical method. Then second application, determination of alpha and k. Alpha, which is called as a degree of dissociation. Degree of dissociation which tells us about the extent of dissociation. Say I know that acetic acid is a weak electrolyte, and being a weak electrolyte it will dissociate partially. Now it will dissociate partially means will dissociate how much? Out of 100 molecules if I am adding, then how many molecules will dissociate? Whether 10 will dissociate, 5 will dissociate, or 20 or 50. It is decided by the alpha value. Suppose I can say that alpha is equal to, generally I can say we use a formula that if I am adding 100 molecules and out of 100 only 10 molecules are dissociating, that is alpha is equal to 0.1. This is the value of alpha. So alpha value can be calculated by using Kohlrausch law. Suppose if it is a strong electrolyte, then for strong electrolyte it is alpha is always equal to 1. But if it is a weak electrolyte, then how the alpha value will be calculated? Then we use this Kohlrausch law. The formula for calculating a weak electrolyte, it is alpha is equal to lambda upon lambda naught, or I can say upon lambda infinity. Now, how we are using a Kohlrausch law? For getting an alpha value, I should know the molar conductivity as well as the molar conductivity at infinite dilution. And for a weak electrolyte, if you wanted to know the value of molar conductivity at infinite dilution, then this can be done only by using a Kohlrausch law, that is application number 1. So to get that alpha value, first I will use that application number 1, and then only I will substitute that lambda naught, and so that we will get alpha value. So the alpha value determination is also based on the Kohlrausch law only. That's why it is a second application. Then K, the K which is called as equilibrium constant. So here I wanted to know the value for the equilibrium constant also. So generally K, if there is a 2 ions are produced, if 2 ions are produced, then K formula is alpha square C upon 1 minus alpha. Generally we use this formula. I got a alpha term. From the alpha, means for getting the value of K, I require the alpha, and C stand for the molar concentration. And if you wanted to know the alpha terms, then alpha formula is lambda upon lambda naught into C upon 1 minus alpha, that is lambda upon lambda naught, which can be written as lambda square upon lambda naught square into concentration upon cross multiply lambda naught minus lambda upon lambda naught. Will get cancelled, and finally we will have a formula for K, that is square C upon 1 lambda is left here, lambda naught, into lambda naught minus this one. So if you wanted to know the value of a K, then for getting a value of K, either we use this formula or we use this formula. Use any of this formula. If you are using this formula, then for getting alpha, you have to calculate lambda naught, which we get from this Kohlrausch law only. And if you are directly using this formula, then again for a weak electrolyte, to get that lambda naught value, we use Kohlrausch law. So this is the second application, that is a determination of alpha and K. Then third application, determination of solubility of a sparingly soluble salt. Now what is sparingly soluble salt? The sparingly soluble salts are those salts which are slightly soluble in water. I can say like AgCl, barium sulfate. These are the salts which are slightly very small amount of when AgCl is dissolved in water. I can say the very small fraction of AgCl get dissolved into the water, while the others remains undissolved. And only since very small number of molecules are getting dissolved, it means only very few molecules are getting dissociated into ions. So sparingly soluble salts are those salts which are slightly soluble in water. Now for the lambda, we have a formula. Lambda is equal to 1000 K upon C. For a sparingly soluble salt, this formula changes. When the salt is a sparingly soluble, then instead of using a term concentration, we use a term solubility. Because when a sparingly soluble salt is added, then the solution becomes saturated, because only a small amount of solute will dissolve. So the solution becomes solution becomes saturated, and in saturated solution, instead of measuring a concentration, we measure solubility, and concentration and solubility for a saturated solution is nothing but the same term. And when the solution is when the solution is containing sparingly soluble salt, then in that case, when the solution is formed, then that solution is called as infinite dilution solution. And infinite dilution solution means a lambda value will be represented by lambda naught, that is molar conductivity at infinite dilution. So if you know the lambda naught value, then you can easily calculate the solubility. So and for getting a lambda naught value for a sparingly soluble electrolyte, like if I have AgCl, then I will use a formula that it is lambda naught of Ag plus lambda naught of Cl minus. So to get that lambda naught value, again we are using the same Kohlrausch law, and once I got lambda naught value, then from this we can calculate solubility also. So for the solubility we have this formula, that is lambda naught is equal to 1000 K upon solubility. So this is Kohlrausch law, and we have these three applications of the Kohlrausch law.